In this video, I will show you the basic of how to relate the equations of motion with the graphs of motion for an accelerating object. From your maths class, you should have learned that if a pair of quantities x and y have a straight line relation in the plot of y against x, they can be related by the equation y equals a constant times x plus another constant. Your maths teacher probably called this y equals mx plus c, the so-called slope-intercept form of a straight line. This name comes from that this first constant m multiplied to the variable x is the slope of this plot, and this second constant c is the y-intercept of the plot. For example, if y and x has a relation as shown in this graph, where the slope is positive 0.5 and the y-intercept is positive 3, then according to this, y and x are related by y equals 0.5x plus 3. On the other hand, if the y and x are related by, say, y equals negative 2x plus 1, this means that the graphs of y plotted against x has a y-intercept of positive 1 and a slope of negative 2. With this y-intercept and its slope, we can easily sketch the graphs of y plotted against x, which looks like this. Let's apply this to a simple vertical projectile motion and we'll take upward as positive. Suppose a stone is initially projected upward at 16 meters per second, and we want to relate its vt graph to its equation of motion. Let's start. Its initial velocity u is upward or positive 16 meters per second, and its acceleration a is that due to gravity, and is therefore downward or negative 9.81 meters per second squared. Using v equals u plus at and putting in these values, we have this. Notice that I have omitted the units inside the equation for simplicity, and so the time t must be in second and the velocity v must be in meter per second. Another point to note is that while we often call this v the final velocity, it's not a must to be literally the very final velocity. Instead, it refers to the velocity at some time t after the initial moment. So it depends on t. It's a variable which depends on the time t you are considering. And this is why the vt graph relates to this equation. Both of them describe how its velocity v changes depending on the time t after the initial moment. Just that this is in graphical form while this is in equation form. But how are they connected to each other? Well, rearrange this equation to this form first. Now pay attention. Since the vt graph has v in the y-axis and t in the x-axis, v is just like y and t is like x. So if v can be written as a constant times t plus another constant, that is the equation of straight line, then the vt graph is a straight line. And you see, this is indeed the case here. V equals a constant times t plus another constant. So according to this, the vt graph must be a straight line. From what you have learned in your maths class, this constant is the slope and this is the y-intercept. So not only can you tell that the vt graph is straight, but also that its slope is negative 9.81 and its y-intercept is 16. With this y-intercept and the slope, we can immediately sketch its vt graph, which looks like this. Let's consider a more complicated equation of motion, the one describing the stone's velocity v with the displacement as it travels, that is, v squared equals u squared plus 2as. Putting these values in, we have this. As we have worked once on a similar case just now, this time I will be more rigorous and include the units in the equation. Before I do any serious mathematical analysis, let me really try some different numbers for s and find the corresponding v. To do this, I rewrite the equation in this form. Here, I have ignored the negative root, which is actually not quite appropriate, but for the sake of simplifying our discussion, let's stick to it. Now, when the displacement s is 2 meters, v is equal to this. Which is evaluated to 14.7 meters per second. That is, when the object is at a displacement of positive 2 meters, its speed is 14.7 meters per second. Similarly, when s is 4 meters, press your calculator and you will have v equal to 13.3 meters per second. That means when it goes higher to a displacement of positive 4 meters, it will slow down to a speed of 13.3 meters per second. We can go on and on with this and get many pairs of displacement s and the corresponding velocity v as shown here. Plot them patiently on the graph paper. And you will get this. Obviously, the Vs graph is not a straight line, but could we have predicted this using some better techniques without going through all the troubles of pressing the calculators to find these values? Of course, we can. In a plot of V against S, V is like Y and S is like X. If the Vs graph was straight, the equation relating V and S must follow this equation of straight line. That is, V must be equal to a constant times S plus an other constant. But is it now? No. Look at this actual equation relating velocity V and the displacement S. As you see, V is equal to the square root of this bunch of things instead of strictly in the form of a constant times S plus an other constant. So, the equation relating V and S does not satisfy the equation of straight line, and therefore, the Vs graph is not straight. What I just told you was that we can tell whether a graph is straight by just looking at the equation, without really plotting the graph like what was done here. This technique makes it so much easier whenever you want to know if a graph is a straight line or not. Now, let's dive deeper into this equation. What if I don't plot V against S, but V squared against S? Wait, what does it even mean by having V squared in the vertical axis? Well, look at this table again. We have computed pairs of S and the corresponding V. If I add a row called V squared to this table, that is, calculate V squared for every V we have here, I have these values. Then plotting V squared against S just means putting these values of V squared in the y-axis and then S in the x-axis. Let's do it. Now this looks like a straight line. But why? Can we prove this mathematically? Note that in the graph of V squared against S, V squared as a whole is like Y and S is like X. If this graph is a straight line, V squared must be equal to a constant times S plus another constant, that is the equation of straight line. Is it now? Observe this equation relating V squared and S. Indeed, V squared is equal to this constant negative 19.62 times S plus this constant 256. It indeed satisfies the equation of straight line. So we can tell that such a strange plot of V squared against S is really straight by just looking at this equation. Furthermore, since you know this first constant means the slope of the graph and the second constant is the y-intercept, you can tell at a glance that this graph has a y-intercept of 256 meters squared per second squared and a slope of negative 19.62 meter per second squared. You see, no detailed computations needed. All that you need is to look at the equation and check out if it satisfies the equation of straight line y equals a constant times x plus another constant. As a remark, I want to emphasize that to study these equations and their graphs, we actually don't need to use any numbers. The analysis is general. By v squared equals u squared plus 2as, we can write it to this form. You may wonder why I am writing things so ugly, but my point here is that from it, I can see clearly the structure of the equation of straight line. That is, as long as this acceleration a is a constant, the plot of v squared against s must be straight. And then the y-intercept of this plot must be u squared and its slope must be 2a. Let's try to solve one more problem with what you have just learned as shown here. Since this problem concerns a plot of s against t squared, we should first search in our mind if we know any equation relating s and t squared. And indeed we have one, that is s equal ut plus 1/2 at squared. And since the car starts from rest, u is equal to 0. Then we have this simplified equation s equals 1/2 at squared. Now compare this with the equation of straight line, bearing in mind that s corresponds to y and t squared as a whole correspond to x. This is certainly a straight line equation with the slope equal to 1/2 a and y-intercept equal to 0. And as observed from the graph, the slope is obviously 50 meter over 20 seconds squared, which makes up to 2.5 meter per second squared, and this is equal to 1/2 a. Solving this equation gives you a equal to 5 meter per second squared, and so the answer is D.